Due to the second law of thermodynamics, we have a basic principle that is any isolated system will evolve in such a way that it's going to approach a macro state with the maximum randomness. So basically what I would like to answer in this video is it possible to go from a random macro state to an ordered macro state for a useful outcome? So how can we make thermodynamics work in favor of such a process? So this is the principle we are dealing with. The basic principle: any isolated system tends to approach a situation of maximum randomness. And we can give some examples for this. For the first example, let's think about the following scenario. I have a weight that is hanging from a pulley, and it's attached to a spindle that will rotate inside water, and as the weight descends to lose a potential energy, WH, this energy will be transformed into rotational kinetic energy of the spindle, which by friction will be transferred into water, and it will heat up the water, and the internal energy of the water increases. The energy will be distributed uniformly over the molecules. So we have the weight W descends. As a result of that, potential energy U is equal to its weight W times h, or if its mass is m, it's mgh, where g is gravitational acceleration. The potential energy decreases, and this is going to cause an increase in the rotational kinetic energy. Rotational kinetic energy 1/2 moment of inertia omega square increases, and due to friction, internal energy, mean internal energy of the water increases. So this is water. And we find that the reason this process is going to evolve in this manner is because finally we have a most random distribution of energy over many water molecules. So we're going from an ordered situation for energy was stored as the potential energy in this object with weight W, and it has now become, at the end of the process at equilibrium, the energy has been redistributed over many molecules of the water, and therefore we have a more random situation. Another example has to do with biological organisms. If you look at the way the life evolves, you have a biological organism that is growing out of highly ordered macromolecules. So if I take a biological organism and enclose it in a box and isolate the system, what will happen to the organism? So if placed in an isolated box, the organism disintegrates. So we will see that it will go to the most random configuration, which will require the organism to disintegrate. So the basic question we would like to ask here is, to what extent is it possible to take a system A from a more random macro state with, so let's call this macro state A, with entropy SA, to a more ordered macro state B with entropy SB. So we have the final entropy is less than the initial entropy of the system. So basically the question we're asking is life possible? Or is industrial revolution possible? So these fundamental questions we can ask by looking at the details of the second law of thermodynamics. So if you remember, we have a system A that is interacting with a system A prime, and the total system A plus A prime, A star, is isolated. And the second law of thermodynamics says it is the entropy of the isolated system that must be increasing, which is the entropy change in system A plus entropy change in system A prime. So this has to be greater or equal to 0. And basically this requirement, due to the second law, does not imply that the entropy of system A must be increasing. So this is not a requirement of the second law of thermodynamics. It's the isolated system entropy, total entropy, that must be increasing. So this brings us to a very important conclusion, and it makes it possible to give the answer yes to the question, life is possible and industrial revolution is possible. It is possible to go from a more random macro state to a more ordered macro state, and that is due to the following principle: the entropy of a system can be reduced only if it is made to interact with one or more auxiliary systems in a process which imparts to these systems at least a compensating amount of entropy. So if you have one auxiliary system the minimum entropy change in the primed system should be minus the entropy change in the unprimed system. If this condition is satisfied, then we can achieve a more ordered macro state. So this is called the principle of entropy compensation. By having the auxiliary system providing an entropy greater or equal to the entropy change in system A, absolute value with a minus sign, we make sure that the total entropy change, delta S star, will still be greater or equal to 0. So this has a few implications. One is that if you look at a process and if you find that the total entropy change, delta S star, is negative following this procedure, such a procedure must be ruled out. So you cannot have a process that has the total entropy change less than 0. The entropy cannot be decreasing for the isolated system. And you may find that the total entropy change is positive for some procedures, but it could be that some procedures could be more practical. Some procedures are more feasible. So how can I tell if a procedure is more feasible? I look at the total entropy change. So delta S star of procedure 1 is greater than delta S star of procedure 2, which is greater or equal to 0. So this may make procedure 1 more feasible. And also some practical requirements to achieve this procedure may make this procedure more feasible as well. So here we have answered a very fundamental question. We know that any isolated system at equilibrium will reach its most random configuration. And you can see some examples here. If a weight descends by a height h, its potential energy will be converted into internal energy of the water through this pulley spindle mechanism, and you will see that the energy will be distributed uniformly over water molecules at equilibrium for most random configuration. A biological organism is growing out of highly ordered macromolecules, so the initial state is ordered, but if you isolate the biological organism, put it in an enclosed container, which is isolated, you will see that the organism will disintegrate to reach the most random configuration. So is it possible to go from a random configuration to an ordered configuration? That decreases the entropy of a system, or basically because life includes ordered macromolecules, industrial revolution involves many ordered systems. We have to make this possible, and the only way to make this possible is to look at the total entropy change, which consists of entropy change of a system A and plus the entropy change of the rest of the universe or the rest of the systems that it is interacting with. So the total entropy change should be greater or equal to 0 does not imply entropy change of our system A should be greater or equal to 0. In fact, the entropy of a system can be reduced only if it's made to interact with one or more auxiliary systems in a process which imparts to these at least a compensating amount of entropy. So the entropy coming from the auxiliary system delta S prime should be at least equal to minus delta S, if not more than absolute value of delta S with a minus sign. So that's called the principle of entropy compensation. that guarantees that delta S star is greater or equal to 0. This is always the case. Now, if you look at a procedure in order to go from a random to an ordered configuration, and you see that the total entropy change delta S star for the total isolated system is less than 0, this procedure must be ruled out. It's not going to happen. And we may find that the total entropy change is more negative for some procedures, or there could be some practical requirements for these procedures, so some procedures may be more feasible than others.